Hello, this is going to be a pretty quick video continuing our work with curved mirrors and the images that they create. This one is on convex mirrors, and the essential question is, how are convex mirrors different from concave mirrors? So you'll probably remember that a convex mirror is sort of the opposite from the concave mirror. It's similarly shaped, but the reflective surface is going to be on the outside. And convex mirrors also will have a principal axis, which is that line that bisects the mirror and splits it into two equal halves, that has a normal line to the principal axis, is a long parallel to the principal axis. And the thing that makes a convex mirror special is that all the light that's coming in parallel to the principal axis reflects outwards as if it came from the focus. So this is similar to how we looked at the concave mirrors, except for this location in space, the light doesn't actually ever get to the focus because it hits the surface of the mirror instead. So parallel light rays bounce out, and your eyeball, if one of those light rays went into your eyeball, would think that that light ray originated at the focus. This is sometimes called a diverging mirror. The word diverging means to spread apart. And you'll notice that when we get those parallel light rays coming in, they bounce out in all directions and spread apart. One note that I kind of mentioned before, that the reflected rays on this never actually come together again. So this is never going to be able to make a real image because those reflected rays are always going to spread out from each other. So the brain always thinks that these images came from somewhere behind the surface of the mirror, and that makes them always virtual. Just like with the concave mirror, the focus is located halfway to the center of curvature. So if that convex mirror was part of a big sphere, wherever the center of the sphere is, the focus is going to be located halfway to that location. Ray tracing with convex mirrors is the same process we've been doing with the concave mirrors and even with the plane mirrors. You can start with your object, one side of the object, so the top of the object, and you could do technically any two rays, but again, there's two rays that are easier to draw based on the geometry that is usually shown in the pictures. Ray number one is this definition of what convex mirrors do, and that is the ray that goes in parallel to the principal axis and reflects out as if it came from the focus. So you just take your ruler and you kind of draw the first line in parallel, and then where it hits the surface, you take your ruler and connect the focus to that location, but don't draw it past the mirror because the ray never actually gets past the mirror. But instead, I draw the real ray reflecting out from the focus, and then you see those little dashes. I'll draw the little dashes in with my pencil behind it because I know I'm going to have to use those virtual rays when it comes to the actual location. The second ray, ray 2, based on the symmetry of light traveling in both directions, does the opposite. That light ray appears to go towards the focus, so you kind of take your ruler and take the tip of the object and connect it with the focus and draw the light ray just until it hits the mirror. And then your real light ray is going to reflect back parallel to the principal axis after you hit the surface of the mirror. And again, I probably will draw in this dashed virtual line behind the mirror because I know that I'm going to need that. So where those two reflected lines, they don't actually ever intersect, right? Because they're diverging. But if they happen to go into someone's eyeballs, your brain would combine that information and think that they intersected. And that location where your brain would think they would intersect would be back here behind the mirror, where we see the tip of that image. Just like with the concave mirrors, any part of the image that is on the principal axis, or any part of the object that's on the principal axis, will create an image in the principal axis as well. So I could do the whole thing again with the bottom of the arrow, but I saved myself some time and just put it right on that axis, right underneath the head of the arrow. So just a reminder, which I already said, but the image is found where the reflections appear to intersect. So, don't get confused by rays intersecting different places. You're looking specifically at the rays that have reflected off of the mirror and where they either intercept or appear to have intercepted. So when you're done watching this video, just like on the last one, I'm going to ask you to go and do a bunch of ray tracing diagrams for convex mirrors to practice them. But I am going to give you the cheat sheet again so you can check your answers. This one's actually easier and more straightforward. All images from convex mirrors are the same. They're all upright, virtual, and shrunken. They might change their magnification, how much it is, but they're always going to be less than 1. And the location of the images will change as well, but they all are going to be upright and virtual no matter what. So I've got here a convex mirror. When I bring it up to the camera, hopefully you can see that image. And you'll notice you're just looking at my computer screen, but you can see the words. That means they are upright. And as I move this thing away, we don't get any of that crazy loss of image when we hit the focus. It's always the same. We keep that same virtual upright image, shrunken image. The amount it's shrunk changes, but otherwise the image is basically staying the same no matter how close or far away the mirror is. All right, so that was a pretty quick one. Review the essential question, which is basically how are convex mirrors different from concave mirrors, and hopefully when you understand the way the shape is and the law of reflection, it makes sense that we get the images that we get. And like I said, you should go and do that convex mirror practice and check your answers. Thanks for watching.